Okay, here's three more equilibrium problems of the ice table variety. Let's jump in. Ammonium hydrogen sulfide decomposes. We have the case of p-value. Don't let that put you off. It is analogous to concentration. And then they want the total pressure in the flask. Well, I guess we'll need the pressures of everything in order to solve that. So why don't we write down what we know? This is a solid and it's going to get omitted. That doesn't make it this times this over 0. It means K sub P is simply equal to this times this. So we omit it. See how there's nothing there? And initially there's no ammonia, nor is there any hydrogen sulfide. It will go up by a value of X. That's simple, right? And we do have the K value. So K will simply equal this times that. And that means that we can take the square root to figure out what each of those are, which is 0.33, but they don't ask for that. What they ask for is the total pressure. Well, there's one each. The pressure will be 0.66 atmospheres. The total pressure is the sum of the partial pressures. In the next problem, we have dinitrogen tetroxide decomposing with a pretty low K sub P value. If the pressure at equilibrium is 0.85, that's good to know. What is the total pressure of the gas mixture at equilibrium? So we want to know the pressures of each at equilibrium. Let's set up what we know. Nothing gets omitted. The KEQ will be equal to this squared over that. And do we have initial pressures? No, but we do know that if they have the one of them, right, the N2O4, and we know that what KEQ is, we can solve for NO2 by first solving for NO2 squared and then taking the square root. And there is the concentration of NO2. That's nice to know. So that's at equilibrium, right? It's at 0.357, and that's our product, so it simply goes up by that value. So the ice table is very helpful there. If this goes up by 0.357 atmospheres, then this must go down by 0.357 atmospheres, giving us our equilibrium concentrations of each, and they want the total pressure at equilibrium, therefore we just add up those two. And therefore, at equilibrium, there's a pressure in the flask of 1.207 atmospheres. Here's another problem that deals with the decomposition of ammonia. They give you the K value, and they want the total pressure in the flask. Okay, well, it will be this times that cubed divided by that. Nothing's getting omitted. If divided by that squared, ammonia squared, agreed? Let's set up our ice table. There's our chemical reaction. We do know that initially, there it is, 3.6 moles. Now, I don't have this set up in terms of molarity, but I certainly could. And normally I did, but let's do it in terms of moles. That's fine. We have that many moles. We do, right? It happens to be a 2-liter vessel. That's fine. And we're going to change this. It'll go down by a value of X. And this will go up by a value of 0.5x, right? Since this goes down a little bit, but for every one that these goes down, these only go down by a half. This could have been everything doubled, minus 2x plus x, etc. But these values should hold. And we now have our equilibrium values, but we're going to do something that they said you could, which is sometimes referred to as the quadratic assumption. Since this thing's really small, then x should be really small. It's not reacting that much, right? This is a very unfavorable equilibrium, so we'll simply assume that that's close enough that it'll be 3.6. And now we can go ahead and plug in to the equilibrium expression because we have values for each of them, right? And in fact, we have some x's there, and that's x to the fourth. So saving you a lot of the math here, you should find that x is 0.0834. As we predicted, a very small value. We can now put that back in, and at equilibrium, this went down by a tiny bit to 3.516. Now, we have to remember that in this case, for reasons that were really unnecessary, but it didn't matter. We did moles rather than moles per liter, so we have to remember that we're dealing with moles, and since we want the concentration, right, that's pressure, we should have moles per liter. And here, they really I think these moles should be atmospheres, right? Since this is all dealing with atmospheres, but this is molar, this is molar, fine, and the total moles at equilibrium is 3.683 moles.